All right, ladies and gentlemen, this class recording has started. So, yesterday, we finished up our qualitative analysis of mechanics by introducing the last concept that we deal with when we're describing motion. So what did we describe, or what did we introduce yesterday? Acceleration. And acceleration is when what happens? Right. Something speeds up, or something slows down, or something changes direction. More generally speaking, all three of those we said were what? Changes in velocity. So our definition of acceleration, right, is the rate at which velocity changes. So we have to have a changing velocity in order for there to be acceleration. And like we just said, changing velocity can take one of three forms: speeding up, slowing down, or changing direction. Okay? Good there. But, as we'll see here as we get into the things today, the changing velocity also has an effect on how far something goes, on the displacement, because that's what velocity affects. So, here's my pep talk for you, okay? This is kind of important pep talk for today and tomorrow, and Monday too, okay? So, today, tomorrow, and Monday, I'm going to do a lot of example stuff up on the board, okay? All the things that we do today, tomorrow, Monday, maybe into Tuesday, we'll see how far it takes, okay? It's all a pattern. I'm going to try to establish the pattern simpler at first, and then we'll make it more complex. But if you don't get the pattern at the first day, applying it day 2 and day 3 are going to be tough, okay? So, when we're doing stuff up here, if I say, does everybody get it? And you don't get it, raise your hand. Stop me. And be like, wait, can you explain that again? I don't see how you got that, whatever, right? Because if I rely on the 4 people that raised their hand, we'll go through it, and I'll be like, oh, everybody's got it. Good to go, right? Okay, but if you don't get it, stop me. And let's make sure we understand this step before we go to the next step. Okay? Good? All right, pep talk over. Here we go.
That was just like a general advice.
There was no pep talk.
No, it wasn't instruction. It was a pep talk.
No, it wasn't.
Because how many times do I like go through class and be like, everybody get it? And all it's just like, then the test comes, guess what? Everybody didn't get it. All right? So, no, what I'm saying is like all the time in class, be like, got it? Good? And everyone's like,
But then like we look at
yeah. That's exactly what you guys look like. You're like, uh-huh, yeah, I got it. And then we take the test, guess what? You guys didn't have it.
all the time.
All right, so establishing the pattern. We're going to actually start with non-accelerated motion. So, if it's non-accelerated motion, what does that mean? It has a constant velocity, right? Just like it says right here. Okay? So let's start with constant velocity, establish some of these things that we're going to use to talk about accelerated motion, but first with non-accelerated motion. So, it says here, sketch shows ball rolling at constant velocity along a level floor. The ball rolls from the first position shown to the second position shown, even though it doesn't actually show that second position, in 1 second. The 2 positions are 1 meter apart. Sketch the ball at successive 1-second intervals all the way to the wall, neglect resistance. So, velocity is a relationship between what 2 things? Nope. Nope. Displacement and time. Alright? Velocity is a relationship between displacement and time. So, for starters, if we look at these 2 pictures, what was the displacement of the ball during this interval? 1 meter. How much time went by? 1 second. Because that's what it told you, because that's what it told you in the little thing that I read to you, and that you have right in front of you. So, what is the velocity of this object? 1 meter per second. That wasn't a trick question, right? Okay? So, if this velocity is constant, right? If we took a picture of the ball 1 second after this one, how far will it have gone?
1 meter.
1 meter. All right? Okay? And then, if we took a picture of the ball 1 second after that, where would it be?
3 meters.
Well, it'd be 1 meter past where it was before. Okay? 3 meters from the starting point. And then 1 second after that, 1 meter. Right? And then 1 second after that, it hits the wall. Okay? Good there. So, part A. Did you draw successive ball positions evenly spaced, farther apart, or closer together? It's not a yes or no question. Okay? So, these ball positions are evenly spaced. Why? Because what's true about the velocity of this object? Constant. And velocity is a relationship between displacement and time. So that means that every time interval, even though mine aren't exactly evenly spaced, sorry, right? Every time interval, it goes the same displacement. Good there? And then to answer B, right, what will be the speed of the ball right before it hits the wall? 1 meter per second. Because that's the speed the entire time. Knowing that, and knowing that this stretch of floor here is 5 meters, how long did it take to get to the wall? 5 seconds. Okay? Good with those. Okay? Alright. Just below that, you have this chart that's telling you speeds, right? Speed is a relationship between distance and time. But in the case of this example, going back to your quiz from 2 days ago, here, is there any difference between distance and displacement? Going back to your quiz from Tuesday. Distance and displacement are the same as long as what's true? It goes in one direction, and one direction only, right? As long as it's in a straight line, distance and displacement are the same. So these are 1 meter of displacement, but they're also 1 meter of distance. Does that make sense? Jafar, if it rolled down the hallway here, hit the wall, and then bounced back, that's when distance and displacement become different. But as long as we only go in one direction, then we have
Just make sure it comes back down to this position,
distance would keep getting bigger,
right?
but displacement would be getting smaller because it's getting back towards its starting point. All right, so for the case of these, as long as we assume that these things are all moving in one direction, right, or only one direction, speed is a relationship between distance and time, right? We said speed is equal to distance over time, right? So, with that being the case, if a greyhound could run 160 meters in 10 seconds, what is its speed?
16 meters per second.
Okay? But then, right, we can rearrange that equation, right? All I did was some algebra to turn this top equation into the bottom equation, right? Okay. So, in this case, if a gazelle can go 1 kilometer, or if it can travel 100 kilometers per hour, but only 1 kilometer, how much time is going to go by? One 1/100th of an hour. Yes? Does that make sense?
Oh, 1,000 kilometers.
And then we can also rearrange this equation, right, to look like this. Right? These are all the same equation, right? We're just algebraically manipulating the order that the variables are in. Okay? And so if we know that a turtle can go 1 centimeter per second and goes that fast for 30 seconds, how many centimeters is it going to go? 30 centimeters. All right, good there? Okay, now, that's for non-accelerated motion, constant velocity. Today, we want to get started here now with accelerated motion. And for our purposes, during this unit, for the rest of this unit, we are going to deal with objects that are undergoing uniform acceleration. Uniform and constant are synonyms of one another. So it's a constant acceleration. So, qualitatively, description, right? Something that's undergoing a constant acceleration would look like what? It's going faster and faster and faster and faster and faster. It continuously gains speed. Okay? Does that make sense? That's what uniform or constant acceleration means. Okay? Now, this example is real similar to the lab that you did last week. Right? It's a marble rolling down a hill. This hill is tilted, sometimes we refer to the hill as an inclined plane, okay? Because it's a plane, right? Like math has a plane and it's inclined, okay? This inclined plane is tilted so that the marble experiences an acceleration of 2 meters per second squared. All right? That's from the tilt of the ramp. Now, ultimately, what's pulling that marble down the hill? Gravity. But gravity always works which way? Down. This isn't exactly going down, right? It's going like down and to the side. So we're not actually getting the full effect of gravity. We'll talk about that in a couple days. But here, a portion of gravity is causing this marble to accelerate at 2 meters per second squared. Okay? Now, yesterday, we talked about this meters per second squared unit, right? And we said that meters per second squared is actually a simplification, right? Does that sound familiar? And it's a simplification of this, right? That sound familiar for yesterday? Okay. So 2 meters per second squared is the equivalent of this. Okay? Does that make sense? Okay. So, first, you got 2 over 1 as the numbers are concerned, right? The 2 over 1 is just 2. That's where the 2 comes from. You're dividing, right? A fraction's division, top and bottom, right? So if you have 2 divided by 1, you get 2. No. Numbers and units different from one another. right? Let's handle the numbers and units differently. So these two parts, right? 2 divided by 1, that gets us the 2 part, okay? But then meters per second divided by seconds, that gets us the meters per second squared part, okay? Does it make sense why those two things are equivalent to one another now?
Yeah.
Okay, now let's talk about what it means physically. What does an acceleration of 2 meters per second mean is going to happen? It's going to speed up every second. How much? It's going to speed up by 2 meters per second every second.
So like, at 1 second would be at 2.
Well, let's go to the chart, okay? So 1 second, if it starts up at the top of the hill, not moving,
0.
1 second later, if we took a little speed gun and took its speed, it would be going 2 meters per second. And then 1 second after that, it would be going 4 meters per second. It's actually 2 times time. We'll talk. We'll do that in a second. Eventually, after how long? No. It's not squared. Right? Hold on. Let's do this. Okay? Hold on. Let's do this first. Then we'll get to the math. Okay? So, 2 meters per second squared, or 2 meters per second means that the velocity changes by 2 meters per second for every second of time that goes by. Okay? This picture here, right? We drew these marbles as it was rolling along the floor. These represent 1 second worth of time, right? We said, okay, a second goes by, how far will it have gone? 1 meter. Second goes by, how far did it go? 1 meter. Because the velocity here was constant. Okay? But if we go here, and now we look at these marbles still represent 1 second worth of time. So each marble is a picture that was taken 1 second after the previous marble. Does that make sense? But what do you see is happening to the displacement of those marbles as these seconds go on? Do you want to answer that question, or do you have a different question? Okay. What's happening to the displacement each second, Jules? Each second they're farther apart. So the displacement from here to here is smaller than the displacement from here to here, and that's smaller than the displacement from here to here. The displacement each second keeps getting bigger. What does that mean about the velocity? It's getting faster because it's going a further distance in the same amount of time. Does that make sense? Okay? All right. Now, let's talk about how much. So, all right. So, I'm going to zoom into this little section right here. Right? Along the bottom, right, you have some V's. So, up at the top of the ramp, right, it says the velocity is 0. Because right when you let the marble go, it's not doing anything. And then, the next marble that's drawn, 1 second later, what does it say that its velocity is? 2 meters per second. Because what happened? How much did the velocity change in a second? It went up by what? 2. Okay? This marble right here is 1 second after this marble. How much will its velocity change in that 1 second? Well, what's the acceleration? 2 meters per second. So how much does the velocity have to change from here to here. Has to change by 2. So it was at 2 meters per second. That means how fast is it going to be going when we get here? 4 meters per second. Because it went up by 2. And that means 1 second after that, how much will it go up by? It'll go up by 2, because that's what the acceleration is. So what does the velocity have to be here? 6. All right? And then, all right, if we keep going down the ramp, all right, it was 6 meters per second here. 1 second later, Jafar, it's going to be 8. And then that means, down the very, very bottom of the ramp, we'll be going 10 meters per second. No. All right, let's talk about what those are. All right. Those are what we refer to, here, let me do this whole thing. Let me grab this picture.
Why not?
That's not how it works.
Why not?
It's just not how nature works. All of these things.
Manipulate nature to do whatever
No,
we want.
you can't
So
manipulate nature.
yes, you can. We're humans.
That's why it's nature.
We're humans. We can do whatever we want.
We just take advantage of what nature does. We're not going to have this argument right now. Okay. All right. So now let's make a point here of something that we introduced before. All right. This 6 meters per second, right, applies to the marble at this particular point in time. That's how fast it's going right there. Okay? So we refer to this that's I think there's something wrong with my computer, Jules. Alright. So that is the instantaneous velocity of the marble at that point in time. Remember we said that instantaneous velocity is how fast something is going at some particular moment in time. An instant in time. Okay? Does that make sense? Do we remember that term? All right.
What do you mean like halfway going 7?
Not half of the distance, half of the time. And, well, at 0.5 seconds, it would be going 1. But, and this is a good point, actually, well, let me do it down here, because this is actually a good discussion, okay? So, they were asking about halfway between here and here. So halfway between 8 and 9, or sorry, 8 and 10, it would be going 9 meters per second. But that's half the time, not half the distance. So if I had to pick a spot where it was going 9 meters per second, it would probably be somewhere there. Not half of the distance, half of the time. Okay? What? We'll talk about that. We're going to get that tomorrow. Okay. All right. Hey, one last thing. Let me finish this up real quick. Okay. So these are nice 1-second intervals, and that's why the time works off so nicely. Okay.
It's not always
But
gonna happen like that.
if we take a look at this, right? See everybody? Okay. Shows up on the test. Whatever. It's okay. At least I got out the door on time. That's cool.
It'll be on the
you know.
study guide. It's
So-
on the test.
All right. So
That's my philosophy.
acceleration is equal to delta v over delta t. But we know that when we talk about delta something, what do we need to know? Change.
Initial and final.
Initial and final. So we can rewrite this to look like this. Right? I'm going to do a little algebraic manipulation on this equation. And turn it into this. Okay? Is that, at least can you kind of see in your head how I did that? I multiplied both sides by t first, and then I just added the initial to both sides. Okay?
That was a.
So with this equation, we can figure out how fast the marble will be going at any time, not just 1 second intervals. So if we want to know how fast it's going at 4.7 seconds, we just plug 4.7 in here. Okay? So this is how we can tell the instantaneous velocity at any point on the ramp. We'll pick it up from there tomorrow.